In the previous video, you already studied the definition of amplitude modulation. Let's just refresh it once again. The definition is amplitude modulation is nothing but a process of changing the amplitude of a high frequency carrier wave in accordance with the instantaneous voltage of low frequency message signal. So now students, if you remember the example that I quoted in the first video, we had considered Hanuman carrying ring. That example I had quoted to you people, wherein Hanuman is nothing but the carrier of the message and the ring is the message. Now students, for any communication to happen, these are the two basic requirements. One is the message itself and the second one is the carrier. Now here what we will do, we will just translate this example of Hanuman carrying a ring onto the electronic terms. So here, instead of the ring being the message, what I will do is, I will take a simple sine wave as a message signal. So you can see here, I have taken a simple sine wave as the message signal, alternatively also known as the modulating signal. And along with that, the carrier, which will be nothing but a high frequency carrier wave. Now students, observe this particular wave. Here, if I consider the positive peak of this signal, it is somewhere here, and if I measure the next positive peak of the signal, it is here. So roughly you can tell that this will be the distance on the time axis. Time axis is nothing but the horizontal axis. So now students, why I'm talking about this is just to give a basic understanding about the frequency. The inverse of this measure when I take, I will get the frequency of the wave. Moving on to the carrier wave, here you can see that the positive peak, if I consider this particular positive peak, the next positive peak is here. So if you observe the distance between these two positive peaks, it's quite very less. And again here also we are taking time along the horizontal axis. So frequency is nothing but inverse of time. So that means by looking at these two cycles, or by observing the distance between these two cycles and between these two, you can easily make out that this particular signal is a low frequency signal, whereas this particular signal is a high frequency signal. And this high frequency signal is nothing but the carrier signal, whereas this low frequency signal is the message signal. Now, what we will get when we add up these two? Add up these two in the sense we are nothing but modulating. So let us just explain it with the help of a different diagram. We will just plot it as a graph here. So now here I have taken the placement of the message signal here, and right below that I have taken the carrier signal. So now I can write this message signal. Since this is nothing but a sine wave, I have given a mathematical representation of this particular function as Vm of t. This Vm of t is nothing but, M here indicates that it is the modulating signal or the message signal. And this Vm of t is nothing but representation of the whole function. Whereas the amplitude of this particular signal is represented by Vm. Amplitude is nothing but, speaking in simple layman terms, we can tell it as the height of this signal, this vertical height, students. So this, the technical term we use for this measure is nothing but the amplitude. So I will consider this amplitude to be Vm, and since this is a sine wave, I am representing it as Vm into sine omega mt. Now the sine omega mt is nothing but the omega mt term what I am using there, it is the representation of angular frequency. And you all have already studied that omega is nothing but equal to 2 into pi into f. Here since I have represented it as omega m, you can take it as 2 into pi into fm, where fm is nothing but the frequency of this modulating signal. Similarly, I can represent the carrier signal using another function Vc of t, where Vc is nothing but the carrier. C represents the carrier signal. So Vc of t is name of the function with the amplitude being Vc. So amplitude here again, it will be the height from this time axis to this particular point. Okay, so this vertical height is what I'm representing as Vc, and this again is a sine wave, so I'm taking it as sine function sine omega ct. Omega c is nothing but the angular frequency of the carrier signal. The breakup of that is omega c is nothing but equal to 2 into pi into fc, and fc here will be the frequency of the carrier signal. So when I do the modulation of this particular signal, what will I get? This is the resulting signal that I get, students. So now, how will I represent this particular signal? That we will discuss about this using the Paint app. So here I have copied the same diagram onto the Paint screen. This is a modulating signal, carrier signal, and the amplitude modulated signal. So let us see now how we are getting this signal. Students, just observe this positive half cycle. The signal, whatever is present here, this positive half cycle, it gets mapped onto this particular signal here. So basically what happens is, if you consider this carrier signal, this is the height of this particular carrier signal. And this is the upper line that I have marked, the upper side amplitude. Similarly, on the negative side, I can have it as roughly almost the same amplitude I'm considering. So this is the amplitude. So now students, just observe this complete, whatever the amplitude of the carrier wave is there, it is the same amplitude that I have roughly marked on this amplitude modulated signal. Now if you observe this message signal, whatever is there, this gets mapped onto this part here. So how exactly it happens is, from here till this point is the positive half cycle of the message signal. So that means it is from here till roughly I can tell this point. Observe this, students. This is how the positive half cycle which is present here is getting mapped onto this side. So this point, if you observe, this is nothing but the amplitude of the carrier signal, and along with that here the positive half cycle is getting added up. Whatever the shape of the signal is there here, the same shape is replicated here. So this is about positive half cycle. What about negative half cycle? This is the negative half cycle, the same thing that is mapped on here. So how exactly it happens is, say I take the negative half cycle, okay, let me take it like this. The negative half cycle begins from here and it is extending somewhere till here. So now here is the negative half cycle. So observe, students, whatever is this one complete cycle, the same cycle is mapped on the carrier signal. But what you're observing is, when the positive half cycle is getting added on with the carrier, the overall amplitude of the carrier that is in this region, it is increasing. Whereas here it is a negative half cycle. That means it is with a negative value. The amplitude of the signal here is negative. And when this negative signal gets added on with this positive signal, it is quite obvious that the effective operation, what happens here, is not addition but subtraction. So accordingly, you can see that the amplitude of the signal here, it is getting reduced. In this particular region here, you can see that there is very little. Let me just mark it like this. See here in this region, you can see that the amplitude of the signal is very little. Okay. Now, moving on to the next part of the message signal, it is another positive half cycle here. So if I have to represent that positive half cycle, observe again, it is extending from this point till this point. So I start the point here and it is extending roughly till here. So that means the positive half cycle is mapped on here. Again, here you can see that the amplitude of the carrier is getting increased because this time the signal is having positive amplitude, and that is why it is getting added on with the carrier. Coming to this part, students, this is again the negative half cycle of the message signal. The negative half cycle has negative amplitude. So again, if I have to map it here, this is the point where the negative half cycle is beginning. Once again, let me just mark the positive half cycle once again. So let's get back to that. Okay, this is the positive half cycle, and after that we will now again start with marking of the negative half cycle. So as we were talking about, the negative half cycle is beginning from here and it is extending maybe roughly till this point. So I can just map it on here. So students, now you're seeing that it is nothing but this complete message signal which is marked on the upper side of the carrier signal. But then you also observe that the negative side of this signal is also changed accordingly, and this is nothing but the mirror image of this upper envelope, or whatever is this message signal, the mirror image of that is imbibed on this side. So now this is the positive half cycle here. So the mirror image of a positive half cycle is quite obviously a negative half cycle. So now what you will get is, observe, from this point till this point will be, this is the positive half cycle. So here I will have the measure, and this I am considering the mirror image of this positive half cycle. So quite obviously it is a negative half cycle. So here I get that negative half cycle. So now coming on to the next half cycle, this is nothing but the negative half cycle. So here if I have to consider the mirror image, students, it will be the positive half cycle. So here, from here till here, I have the distance. This distance is what I'm mapping now, and this is the positive half cycle. Similarly, next again if I map it, I will have it for the next, this positive half cycle. So mirror image of this is nothing but a negative half cycle. The cycle extends from, one second, let me just correct this off. Okay, and moving on to the next one, it is from here to this point. So here, this is the mirror image of this positive half cycle, which is nothing but the negative half cycle. Now this is the last one, that is the negative half cycle. Mirror image of that is nothing but a positive half cycle. The distance will be from here till here. So if I lift this, this becomes the image. So now students, just observe here, at the upper end I have the message signal mapped on, and at the lower end I have the mirror image of the message signal that is being mapped. And students, these two lines which is drawn, it is nothing but an imaginary line which I drew so that it becomes easier for you people to understand with reference to this time axis. So if I talk with reference to this particular time axis, the signal is swinging around this time axis. So accordingly, this is the representation of this time axis. And here on the negative side, this is that imaginary time axis which I have taken, and the signal is swinging around this particular imaginary time axis. So now, observing the signal, you can see that at any given instant of time, say for example, I will pick up say the signal at this particular instant. So here the signal is having the maximum amplitude and we represent the amplitude as Vm. So now here if I talk about this particular signal amplitude, just observe this amplitude is getting added on with the corresponding amplitude of the carrier. So if I consider the amplitude of this signal to be Vm, the amplitude here is Vc. So the overall amplitude at this particular point will be nothing but Vm, which is measuring till here, and from here on it is Vc. So it is nothing but Vm plus Vc. Observe this, students, it is Vm plus Vc. So the total amplitude is nothing but the sum of the signal, that is modulating signal, and another signal, that is carrier signal. Talking about, say for example, I will talk about this particular instant. Now here also at this particular instant I have the message amplitude, which is so much, carrier amplitude so much. So both of them are getting added on here. Observe, this is the amplitude, a very small amplitude of the message signal, and the complete amplitude of the carrier signal. So that means the total amplitude is nothing but from this point to this point. Similarly, students, now if we check the amplitude of the signal at this negative part of the cycle at this particular time instant, this is the amplitude of the message signal, and the amplitude of the carrier at that particular point will be so much. So now effectively what happens is this amplitude gets subtracted from this amplitude. I repeat, this amplitude gets subtracted from this carrier amplitude. So here if you observe the overall carrier amplitude at the same time instant, here I am representing the overall amplitude will be so much, but the message signal from here till here, I'm just representing the line at the different place because I can't mark it on that, students. So this is nothing but the message signal amplitude, which is actually subtracted. So the effective signal amplitude will be, let me take say this color and represent. So the effective signal amplitude will be only so much. So you can see that this complete area, in fact, this complete curve, whatever you observe, at every point here, actually what is happening is the message signal is getting subtracted from the carrier signal. So that is why in this complete location, you can see that the carrier amplitude is getting reduced. Now, this signal, what we obtain in this shape because of the combination of these two signals, this is known as amplitude modulated signal. So this amplitude modulated signal is nothing but the resultant of this modulating signal and this carrier signal. When these two signals undergo modulation, particularly when they undergo amplitude modulation, the resulting signal is something like this. So now students, you have understood that how we have obtained this amplitude modulated signal. So if I have to represent this amplitude modulated signal using a mathematical expression, then this will be the expression wherein this complete term Vc plus Vm of t is nothing but a representation of the amplitude modulated signal. This is the amplitude modulated signal represented by Vam, and the amplitude of this signal, it is represented by Vc plus Vm of t. What is this Vc plus Vm of t? Students, you already know Vc is nothing but amplitude of the carrier, and I told you that the amplitude of carrier gets added on with the amplitude of this signal, but then the amplitude of the modulating signal keeps on continuously varying as a function of t. So that is why I have taken here as Vm of t. So that means amplitude of the amplitude modulated signal is nothing but the carrier amplitude, which is constant, plus Vm of t, which is nothing but varying as a function of t. So at given point of time, the time could be something here, the time could be somewhere here, time could be somewhere here, it could be at any point of instant on this time axis, represented by Vm of t. And also this signal is a sine function, and if you observe, the frequency of this signal is nothing but matching perfectly with the frequency of this carrier signal. So that is why here we are taking the term sine omega ct. Now sine omega ct, in this omega c is nothing but the angular frequency of the amplitude modulated signal, and omega c is nothing but equal to 2 pi fc. Again, fc is nothing but the carrier frequency. So this is the expression for the amplitude modulated signal. Students, now we will move on to a very important term, that is modulation index. Modulation index is nothing but a measure which tells us to what an extent is the carrier modulated. There are other names for modulation index. It is also known as modulation factor or depth of modulation, and it is represented using the alphabet small m. Since we are talking about amplitude modulation, I have given a subscript here as small a. So MA is nothing but the representation or the symbolic representation of the modulation index in case of amplitude modulation. So now, as I told you, it tells the extent to which the carrier is modulated, and this is given as or represented as a ratio of Vm by Vc. Vm is nothing but the amplitude of the message signal, and Vc is amplitude of the carrier signal. So here MA is nothing but the ratio of Vm by Vc, and it is always very much essential that this ratio should always be less than 1. That means the value of MA should be anything between 0 and 1. Now, this also tells that to maintain this value as always anything between 0 and 1, the necessity is that Vc should always be greater than Vm. So this is the basic condition for effective amplitude modulation. Now, why it is an effective condition, we will discuss it very shortly. But before that, let me tell you another important thing, students. This MA, that is modulation index, is normally expressed in percentage, and hence it is also known as percentage modulation. So two important points to remember here. One, MA is nothing but the ratio of Vm by Vc, where Vm is always less than Vc, and this particular value of MA can also be represented in terms of percentage, and then it is known as percentage modulation. Now, let's just look into the point that why should MA be always less than 1? I told you that for effective modulation, the value of MA should be always between 0 to 1. In case the value of MA exceeds 1, that time it results in a distortion which is known as overmodulation. If the carrier is overmodulated, it results in distortion, and as a result of this distortion, a part of the information is lost. Now students, just observe in this diagram. Here this is a complete amplitude modulated signal, and in this particular region, if you see, the amplitude of carrier is constant. That means it is simple, there is no message signal here. So here there is no modulation that is happening. Modulation is beginning from this particular point of time. And here if you see, this is the swing of the message signal. This is the positive half cycle, and here is the negative half cycle. So here you can see that this negative half cycle is less than the overall amplitude of the carrier signal. That is why you can see that still there is some amplitude of the amplitude modulating signal existing here. Now this is a condition if the value of Vm, that is amplitude of the message signal, is less than the amplitude of the carrier signal. Now what happens in case if both are equal? That means condition where Ma is nothing but equal to 1. Now come to this second diagram, students. Observe here, this is the positive half cycle. This is of course the region where there is no modulation. So modulation is beginning from here. This is the positive half cycle and here is the negative half cycle of the message signal. So in this particular region, students, you can see that the amplitude at this particular point of time, it is almost 0. That means here the amplitude of the message signal is equal to the amplitude of the carrier signal. And I told you that at this particular point of time, what happens is the amplitude of the message signal gets subtracted from the carrier signal. And this is the peak of the negative half cycle. Let's just get back to the Paint app and discuss that again. Now here we will consider a signal, that is a modulating signal, which has slightly greater swing than the current signal. So say for example, this is the signal that we are taking. So if I consider this swing accordingly, here what happens is this particular portion, it will have a greater swing here. Something like this. And talking about the negative half cycle, the swing will be say increased so much. In that case, what happens is in the negative half cycle, students, observe carefully, the signal will come till here. So you can see that the negative half cycle is almost touching the time axis of the amplitude modulated signal. This condition occurs if the amplitude of the message signal is equal to the amplitude of the carrier signal, resulting in the value of Ma equal to 1. So the percentage of this is nothing but 100%. Now, this is the maximum amount of modulation that can be achieved. In case, students, if Vm becomes greater than Vc, that time what happens is this signal exceeds the time axis and comes below here. So here you can see this particular region wherein the signal is crossing this time axis and it is coming onto the negative side of the particular signal. So now similarly, if I talk about the lower portion of the signal, what happens is accordingly in the negative side also extending from here to here, you will have the signal crossing like this. So the resultant is that in this particular region, the positive and the negative signals, they will cancel out with each other and hence the complete signal is getting chopped off or it is getting cut off or the signal is getting distorted. So in this diagram, you can see that the signal is completely cut off from this portion till this portion. That means the signal which had to be continuous like this, the modulating signal which should have had the continuous envelope like this, it is not existing here. It is coming till here and here the envelope continuity is lost. Then again it is beginning from here. So this region is known as the distorted region and here the information will be lost. And this type of error occurring is known as overmodulation. In this, what happens is the information which is present at this particular time instant will be completely lost. So that is why always it is a basic essentiality that the modulation should not exceed 100%, or the value of MA should always be anything less than 1 or at max equal to 1, but never ever greater than 1. In this particular diagram, the modulation is represented in terms of percentage. For example, in the first diagram, you can see that the modulation percentage is 50%. So in case if I have to represent the value of MA in normal numbers, it is nothing but equal to 0.5. In the second case, where there is 100% modulation, the value of MA is equal to 1. And in the third case, wherein I have shown overmodulation, the percentage modulation is 150%. That means MA value is equal to 1.5. Now, this particular diagram is quite an important one, as it can be targeted for either 2 marks or 3 marks. Students, with this, we come to the end of the video of this particular session. See you soon with the next video. Bye.